Okay, so whenever I teach an intro programming class, there's kind of like this spiel I like to go through. And what it is, it's about sort of how computers work at a very high level and how different languages interrelate to each other and sort of where they fall on the spectrum, right? Okay, so what computers are they're just machines, right? So if we go really deep inside a computer, what we'll find are just wires, essentially, right? So there'll be wires, and sometimes they'll have an on state, which is generally 5-ish volts, and sometimes they'll have an off state, which is basically 0 volts, right? So the upshot of that is that we can perform operations on those states, and we can get things like math to happen, right? And once we have math, we can get all sorts of cool stuff, all the great games and applications and wonderful tools that make modern life so cool, right? But in order to program a computer, what we have to do is we're telling it what to do, right? And all computers understand are on and off, right? That's all they get, just those high and low states on wires, right? So if we go really deep in the computer, there are specific circuits that have specific um, functionality to add two numbers, to subtract two numbers, to do other very simple operations, right? So, we crack open a computer, we can go deep, 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 and we find the central processing unit, or the CPU. Inside of that, there's something called an ALU, or arithmetic logic unit. But, that's not all that important. What's important is that at a fundamental level, what a computer does is it interprets on and off states, sequences of on-off states, and then takes action on them using specific bits of hardware, ultimately, to produce new on and off states, right, that are meaningful. So the task of a programmer is to give the computer instructions. So in the very early days of computing, the only way to give a computer instructions was basically flipping switches, essentially, or doing something like that, where you're basically feeding in, you're directly controlling the states on wires in some very sort of direct way to get the outcome that you want, right? So that is really hard. And one step up from that is something called machine language. So machine language is kind of the lowest, closest to the metal thing that happens in modern times, right? It's been around for a while, and so let's say we want to add two numbers, right? So in normal sort of language or math, right? We do something like this. We just say 2 plus 3, right? And we all understand what that means. We just take 2 and we add 3, right? And we know that that's 5. So if we want to do that on a computer, though, and we want to tell a computer to do that or ask a computer to do that in a way that it would understand, this is what it looks like, sort of as close to the metal as you can get realistically. It would look something like this. Just going to write it out, and we'll talk about the wonder that is close to the metal operations. Okay, there we go. Super clear, right? So what this is something called assembly language. So what we have is over here we have MOV, and then we have EAX, what's that? And then 2. Then we see MOV again, right here. And this time we see EBX, 3. And then we see one thing that finally makes sense, right? We see add, EAX, EBX. So what's going on here is, this isn't too important, but the only reason, I always like starting here, because this is kind of as close to what a computer can understand as humans tend to get nowadays, right? So this is something called assembly language. And what we've got is this MOV, and add is an instruction, and it corresponds basically to a specific sequence of bits. So this gets translated in a very direct way for a machine. And then these EAX and EBX, what those are they're little pieces of memory, kind of. So they're a place in the computer. So what we're doing here is we're moving 2 into EAX, which is a place in memory. And then we move 3 into EBX, and then we add those 2 places, right? And so we've added 2 and 3. Now, just as an aside, these EAX and EBX, There's something called registers. They're definitely not places on your hard drive, and they're not even in RAM. They're on the actual CPU itself. So again, I don't. The reason I always start here is just to show you this is what we would have to do if we wanted to talk to a computer directly, and this does happen sometimes. This is assembly language does get used, but it's a little hard, right? That's a little hard to think about. So that's what you have to do if you want to talk to a computer directly. But luckily for us, there are better options. So in the sort of middle of the 20th century, there was this woman, Grace Hopper, who luckily for all of us invented something called a compiler. So Grace Hopper was amazing. She did a lot for computer science. I highly recommend checking her out. She's got a great interview on David Letterman that's definitely worth watching. But upshot is that she invented the compiler. So what's a compiler? Well, what a compiler does is it lets us write code in something a lot closer to English. So I'm going to write some code that does the same thing. It's going to add 2 and 3, but it's going to be, this time it's going to be in C++ code. So okay, so here we have the same idea. We're adding 2 and 3, but it's different, right? So we have this one word, int, and then we say result equals 2 plus 3 semicolon. Now there's some stuff going on here, right? There's some things that we can unpack this quite a bit, but the important thing I want to get across is that this is valid C++ code. This would work. However, this doesn't mean anything to a computer. This, as written, does not work, right? Because it's not machine code. It's not on and off. It's not the binary instructions that a computer can understand. So what has to happen is this perfectly valid little bit of C++ code gets translated into something that the computer can use. And that translation process is called compilation, right? So let's say that I only speak English, which is unfortunately true. I wish I spoke another language. And I write a novel, right? So I write a novel in English, and I want to sell it in France. So let's just, for simplicity's sake, let's say that I want to, people in France don't speak English. So what has to happen? I have to take my novel, this entire big work, right? And it has to go through some translation process to become a French version. So what I would probably do is I would ask some translation service to please take my book and translate it from English to French. And at that point, I would get something that I could no longer read, but a French speaker could read. And that's what happens when you compile a program. So you take something that is still, it has to be very carefully written and has to obey the rules of the language you're using, but it's a lot more like a natural language. It's a lot easier to think about. Then that goes to a program called a compiler, and that compiler takes everything you've written and generates a version that the computer can actually use. So once you've done that, you have something that the computer can run. But the flip side of that is the output from the compiler is not something you can read anymore. Right? So now I'm simplifying things a little bit. You definitely can reverse engineer. There are ways to get at it, but essentially, for the most part, once you've compiled something, it's done. You don't touch the output ever. Right? So let's say I write a novel, and I'm racked with guilt because I treated my main character horribly in the end. Right? So I decide, I really want to give it a happy ending. So what do I have to do? Well, if I wanted to sell that novel in France again, right, I would have to go back to my original English. I would have to change something about the book, right? Then I would have to send it to that same translation service again. And once I had done that, I would get another version that, once again, I couldn't read anymore, right? Because it would be exclusively in French. But then that new version would be ready to be distributed in France, right? So that's how compiled languages work. So you write, you do a lot of work in something that you can read, but the computer can't. Then you run it through a compiler, which generates something that the computer can use, but you can't anymore, right? And to make changes, you go back, you change your source code, and then you compile again. So that's how compiled languages work. So the most common compiled languages are C++ and Java. Java, now this is kind of my personal opinion, right? But Java's still out there. There's a lot of Java code that is still being run, but I wouldn't really recommend spending a lot of time on Java now. It's kind of in decline. C++, on the other hand, is still enormously important, and a very large proportion of the software that people come into contact with on a day-to-day basis is written in C++. So C++ is fantastic. It's a really great language to know for a lot of reasons, and for a compiled language, that's kind of what I recommend everybody kind of focus on, right? So so let's just to recap a little bit. We started at this a long time ago. There was like basically just flipping switches and punch cards and etc. Right? So up from that, we had machine code. Now that was better, but still a little hard to work with, right? Now one step up from that, we have compiled languages. Now what I mean by one step up is each level up we go, right? We increase the amount of abstraction between what we're working with and the actual machine itself. Now that's both good and bad. It's bad because it's adding more overhead, right? So there's more translation that has to happen, and it's possible that your code can end up running slower as a result, right? So that's the downside, right? The upside though is, as you can probably imagine, if you try to write any large-scale application in machine code, it's going to be very, very hard. It's going to be very hard to do. It's going to be very hard to extend. And it's going to be very hard just to think about, right? So people have done it, and that's very impressive. But it's generally, you don't really want to do that unless you really, really need to. So, and I should also say that the modern compilers are pretty good about sort of optimizing your code as it goes in that translation step from what you wrote to something the computer can use. So it's a little bit as if that translation service not only just translated my novel directly from English to French, but they also kind of changed it a little bit to make it a little more appealing to a French audience. So modern compilers are doing a lot to kind of optimize things behind the scenes. So the actual output is really pretty much as good, for the most part, as if you really did write the entire thing in assembly, which would be kind of a nightmare for anything of scale, right? So that's compiled languages, but we can go one step further up, right? So let's say that, just to continue with sort of this idea of English and French, right? So let's say instead of writing a novel that I want to sell in France, I'm in the same room as a French speaker. So I only speak English. I'm in the same room as somebody that only speaks French. So if I want to have a conversation with that person, probably what I'm going to want is for there to be a third person in the room that serves as an interpreter, right? And in that case, I would say something in English. The interpreter would translate that into French, right? The French-speaking person could say something in return that would get translated back into English, right? So there's this intermediary person that's translating sort of in an interactive way. So that's kind of how an interpreted language works. So with an interpreted language, there's another program, just like the compiler is a program. There's a program called an interpreter. And what an interpreter does is it does kind of that, right? So you give it little bits of code at a time, and as it's fed code, it translates that into machine code, right? So the big popular interpreted languages are JavaScript, Python, Ruby, etc., right? Now, so, again, we're up a little higher in abstraction, right? So interpreted languages potentially are a little slower, but they're potentially a little easier to use too, right? Because there's a little more abstraction going on. So really, any real engineer is going to need to know both. So, I always, if you're getting started in programming, or even if you've been doing it for a while, everybody really should strive to know at least one compiled language. C++ is definitely what I recommend. And at least one interpreted language, which JavaScript is definitely what I would recommend there. It's kind of already important, and it's becoming more important every day. So if we continue to go up levels of abstraction, you can go up from there, but then you pretty soon you get out of programming altogether, right? So you go too much more abstraction levels above interpreted languages, and then you're getting kind of to just structured data, which is also really important. But then we're talking about things like HTML or XML or SVG, stuff like that, right? And that stuff is all really important, but it's not programming. It's just structured data, which is really important. If you're going to be an engineer, you need to know those as well. You need to be familiar with HTML, XML, JSON is really important too. But it's not programming, right? It's just data. So yeah, so I mean I'm glossing over a lot in that, but I always like starting out there to just give people a little bit of an idea of sort of what these different layers are of machine code, assembly, compiled languages, interpreted languages, and then other stuff, right? And again, as you grow in engineering, you definitely want to know a compiled language and interpreted language. I definitely think there's a lot of benefit to be had in diving into assembly a little bit too. It's not necessarily something you're going to actually use directly on a day-to-day basis, but it's a really good tool for kind of training your mind to think like an engineer. So it's something worth doing, and it has its own elegance about it that's kind of hard to describe if you haven't played with it, right? But yeah. Okay, so that's kind of my 1,000-mile up overview of programming and programming languages. And yeah, see you in the next video.